The following moles and titration question taken from an ATP past paper from O levels is about finding the water of crystallization X in this sample. So the question reads that iron 2 sulfate crystals have the formula FeSO4.xH2O, where it's a hydrated salt. So there's water in it, and we need to find out what is the mole ratio of the salt and the water molecules in the crystal, where X, and he's also said that X is a whole number. Now, a student determines the value of X using aqueous 0.02 mole per dm³ potassium magnate 7. So again, it's a redox reaction, and he has said that potassium magnate 7, which is purple, oxidizes iron 2 ions to iron 3 ions. So KMnO4 is a very strong oxidizing agent. It's going to oxidize iron 2 ions to iron 3 ions, and he's also given the color of this potassium magnate 7, plus the concentration of potassium magnate 7 is also given to us. It's called solution F. Now, starting with the first part, the question states that a sample of iron 2 sulfate crystals is added to a previously weighed container, which is then reweighed. The mass of the container is plus the crystals is given. It's 10.94 grams, and the mass of the container is also given. So you are asked to calculate the mass of iron 2 sulfate crystals used in the experiment. So we're going to subtract 5.98 from 10.94. We're going to get rid of this mass of the container from 10.94. So using my calculator, it's going to be 10.94 minus 5.98, and the answer that I'm getting is 4.96 grams. So that is going to be the mass of the crystals of FeSO4. Let's write that down as well. The original crystals of FeSO4.xH2O, these hydrated crystals, have a mass. The mass that is taken in the experiment is 4.96 grams. In the next part B of the question, we are told that the student transfers the sample of iron 2 sulfate crystals to a beaker. So he's first transferring, he transfers the sample of iron 2 sulfate crystals to a beaker and adds 100 cm³ of dilute sulfuric acid. This solution is made up to 250 cm³ of distilled water and is mixed well. So we're going to show this on in a sketch. We're going to draw a small sketch and show the steps that have been performed in this paragraph over here. So here is our beaker, and we're going to add FeSO4 4.96 grams into this beaker, followed by we're going to dissolve this FeSO4, the hydrated salt, in sulfuric acid, and he's saying that adds 100 cm³ of dilute sulfuric acid. So that would be added, and a solution would be formed. You're going to mix this FeSO4. Remember that there would be no reaction occurring. FeSO4 and H2SO4, they don't react. You're only using this acid to dissolve this salt. So this salt is being dissolved in an acidic solution, and once the salt is dissolved, it's transferred to a volumetric flask. The solution is made up to 250 cm³ of distilled water. You always use a volumetric flask to make solutions with volumes of 250 cm³. So here is my volumetric flask. I'm going to transfer this solution into this volumetric flask. So this solution is then transferred to this volumetric flask, where by adding distilled water you dilute this solution and make a 250 cm³ solution. Remember, a volumetric flask has only one mark, which is the 250 cm³ mark. So by adding distilled water, I've diluted the solution and made a solution that has a volume of 250 cm³, and this is called this is solution G. So this is called solution G. So I'm going to label this. It is solution G. And what does it contain? It contains the dissolved FeSO4, the 4.96 grams FeSO4 in aqueous state now, because now it's dissolved. So this is FeSO4 aqueous, and this is my solution. In the next part, the question states that using a pipette, 25 cm³ of G is measured into a conical flask. So now you're transferring this solution G. So this solution G is now being transferred to a volumetric flask. So let's draw a volumetric flask. So here is my volumetric flask. I'm going to transfer 25 cm³ of this solution into this volumetric flask. 25 cm³ of solution G into this volumetric flask. What does it contain? It contains FeSO4 aqueous. but only 25 cm cube is transferred. This was a 250 cm cube solution G. We only transferred 25 cm cube into this conical flask over here. So this is done. 25 cm cube G is measured into a conical flask, and then F is put into a burette and run into the conical flask containing G. So we're now going to draw a burette now. So here is my burette, and I'm going to put solution F in the burette. And what was F? F was very initially mentioned in the early stages of the questions, in the first few parts. F is 0.02 mole per decimeter cube potassium magnate 7. That's F. So it has the concentration is also given for F. It's 0.02 mole per decimeter cube. 0.02 mole per decimeter cube. The concentration is known, and we also know what it is. It's potassium magnate 7, which is KMnO4. So KMnO4 is put into the flask, and a titration is performed. So F is put into a burette and run into the conical flask containing G. So there's going to be a titration reaction that's happening, KMnO4 being added, and it's going to react with the FeSO4. And he's also previously told us that FeSO4 gets oxidized when you add KMnO4. So KMnO4 is being added from the top, and he's also given us the color of KMnO4. KMnO4 was had a purple color, and when this purple colored KMnO4 reacts, it turns colorless. So this solution, in the next part, is asking what is the color of the solution in the flask before F is added. Before F is added, the solution over here, 25 cm cube G, contains FeSO4. Remember, FeSO4 is green in color. It's a green solution. Fe2 plus ions, when they are aqueous, they form a green solution. So initially it's a green solution. When you start adding KMnO4, this purple color is going to fall into this FeSO4 solution, and as soon as KMnO4 falls into the solution, it reacts and it changes to colorless. Whenever KMnO4 reacts, it changes from purple to colorless. So when the reaction is happening, the KMnO4 would fall into the flask and it would keep on changing to colorless. But when all the FeSO4 has been used up, that is the point, that is the end point. When all the FeSO4 gets used up, if you still keep on adding KMnO4, the KMnO4 would not react because there's nothing to react with, and it would remain purple. So at the end of the day, at the end point, the KMnO4 stays purple. So the flask over here has no more FeSO4, and you keep on adding KMnO4, the purple solution would fall into this flask and it would start changing this solution and give it a purple color. So at the end point, that is the end point. That is the point where you should stop adding KMnO4. So that is your end point. Initially it's green and it changes to purple. Now for this titration, the volume of KMnO4, the next part of the question, part C, states that the student does 3 titrations. The reason 3 titrations are done is to improve accuracy. More titrations give you a better average result, so it would improve the accuracy. And the diagram below show parts of the burette with the liquid levels at the beginning and end of each titration. So he's given you pictures of this burette for 3 separate experiments. 3 separate experiments are performed, and we're going to find out what volume of KMnO4 was actually added into this conical flask over here. So if you look at the first titration, the initial burette reading and the final burette reading are given. The initial burette reading is 0 centimeter cube and the final burette reading is 28.8 centimeter cube. So he's given us a table after that as well, so we need to fill this table. So the initial burette reading for the first titration was 0.00 centimeter cube, and the final, if we go back and have a look, that is 22.80 centimeter cube. So it's 28.80. It's actually 22.80 centimeter cube. So that's the initial and final burette readings for the first titration. Now if you look at the second titration, the initial burette reading is 17.50 centimeter cube. So we're going to write that down as well. So the initial burette reading is 17.50 centimeter cube for the second titration, and the final burette reading in the picture is 39.70 centimeter cube. So that's 39.70 centimeter cube. And now let's look at the third titration reading. The initial burette reading is 8.90, so that's 8.90 centimeter cube. And the final burette reading in this is 31.30 centimeter cube. So that's the final burette reading, which is 31.30 centimeter cube. Now we need to calculate the volume of F added in each of the experiments, the first titration, the second titration, and the third titration. So it's going to be the difference between the initial and final burette reading. So for the first titration, the answer is going to be 22.80 centimeter cube. Moving to the second titration, it's going to be the difference between these two values, the final and the initial. So using my calculator, it's 39.70. So it's 39.70 minus 17.50. And the answer that I'm getting is 22.20 centimeter cube. And the third titration reading is going to be, it's going to be the difference, 31.30 minus 8.90, and the answer is 22.40 centimeter cube. So I've gotten three titration results. These are for the volume of KMnO4 that's being added, three separate experiments. So we're trying to find the volume of F, or volume of KMnO4 that's being added into the conical flask. So three separate titration experiments are done, and we have found three separate volumes. The first titration shows 22.80 centimeter cube, the second 22.20 and 22.40. Now we have to take the best titration results. The best titration results are the ones that are close to each other. So these two values, 22.20 and 22.40, are close to each other. This value is slightly off, which indicates that there must be something wrong going on in that experiment. So the values that are close together are more consistent, and then they would be considered to be more accurate. And in the last part, using these results, we need to find the average volume of F that's being used. The average volume of F is going to be, we're going to take the average of our best titrations. So it's going to be the average of 22.20 and 22.40, and I'm going to divide that by 2, and the answer that I'm going to get is 22.30 centimeter cube. And I'm going to add that on my sketch as well, that the average volume of KMnO4 that's being added is 22.30 centimeter cube. So that is the average volume of F that's being used in the three experiments, and the concentration of F is known and the volume is known. Now if the concentration and volume is known, you can find the moles of F. So in the next part, you are precisely asked to find out, figure out, or calculate the number of moles of KMnO4 present in the average volume of F. So we need to find the moles of F. Moles for solution is concentration multiplied by volume, and the concentration is known. We know that F is 0.02 mole per decimeter cube KMnO4, and we also know the volume, which is 22.30 centimeter cube. So using my calculator to solve this volume needs to be in dm cube, so I'm going to divide that by 1000. So now putting the values in the calculator, the answer that I'm going to get is it's going to be 4.46 times 10 to the power minus 4 moles of KMnO4. So the amount of quantity, so let's go back to our diagram. The amount or the quantity of KMnO4 that's being used is 4.46 into 10 raised to the power minus 4 moles. So I've added the value of KMnO4 that's being used, 4.46 into 10 to the power minus 4 moles over here in this sketch over here. So the amount of F that's being added from the burette is going to be, let's circle that as well to highlight this. So the quantity of moles of F or KMnO4 that are being added are 4.46 times 10 to the power minus 4 moles. These are the quantity of moles of KMnO4 that are added to the flask, which contains FeSO4. And in the next part, the question states that in part E, 5 moles of FeSO4 are going to react with 1 mole of KMnO4. So they've given you the ratio in which KMnO4 and FeSO4 react. 1 mole of KMnO4 reacts with 5 moles of FeSO4. Now in our question, we're using 4.46 times 10 to the power minus 4 moles of KMnO4. So what would be the amount of moles of FeSO4 that would react with that? So on the sketch over here, we can add this on the sketch over here as well. So if you have 1 mole of KMnO4, it's reacting with 5 moles of FeSO4. So that's the ratio. So if you have 4.46 times 10 to the power minus 4 moles of KMnO4, then the quantity of FeSO4 that would react with it according to this ratio would be 5 times that quantity. So using the crisscross method, using simple ratios, the quantity of FeSO4 that would be needed would be 4.46 times 10 to the power minus 4 moles multiplied by 5. It's going to be 5 times that amount. So using my calculator, the value that I get is going to be 2.23 into 10 raised to the power minus 3 moles. So let's put that quantity, that's the amount of FeSO4 that you have, 2.23 times 10 to the power times 10 to the power minus 3 moles. So that is the amount of FeSO4 that's present in this 25 cm cube sample of G. And in the next part, part F, you're now asked to calculate the number of moles of FeSO4 present in this original 250 cm cube solution. So remember this original solution that we made. The original solution was a 250 cm cube solution that contained FeSO4. And we only titrated 25 cm cube of this. And what we know is that the 25 cm cube solution in this flask over here contains 2.23 into 10 to the power minus 3 moles of FeSO4. So if 25 cm cube contains these many moles, so the original 250 cm cube solution would contain how much moles? So that's again simple ratios that we know that 25 cm cube contains 2.23 times 10 to the power minus 3 moles. So what would be the quantity in 250 cm cube? How many moles of FeSO4 would be present in 250 cm cube? So using simple ratios, the quantity would be 10 times this value. So it's going to be 2.23 into 10 raised to the power minus 3 multiplied by 10. So this is the quantity of moles that would be present, because 25 cm cube and 250 cm cube you need to multiply by 10. So the number of moles is also going to be 10 times that amount, which is going to be equal to 2.23 into 10 raised to the power minus 2 moles. So this over here would be your answer. And let's put that on the sketch as well. The amount of moles of FeSO4 in this flask over here is going to be 2.23 times 10 to the power minus 2 moles. And where did all these moles of FeSO4 come from? They're basically coming from we found the moles of FeSO4. All these moles were coming from this hydrated salt that we dissolved initially. So in the next part, you're now asked, using your answer to F, calculate the mass of FeSO4 in the original sample. So we have the moles of FeSO4, which is 2.23 times 10 to the power minus 2 moles. And moles is equal to mass divided by the molar mass, the MR, so we need to find, using your answer to F, calculate the mass of FeSO4 in the original sample of FeSO4. So we need to find the MR of FeSO4, which is going to be Fe is 56, sulfur is 32, and there are 4 oxygens. So that is going to be 4 oxygens are going to be 16 into 4. That would be 64. So using my calculator to find the mass, it's moles is equal to mass divided by MR. So mass would be moles multiplied by MR. And the answer that the calculator gives is rounded to 3 significant figures. It's going to be 3.39 grams. So that's the mass of FeSO4. So it's only the mass of FeSO4, not the water. So going back to our sketch, originally we took a sample that had a mass of 4.96 grams. So including the water, the salt had a mass of 4.96 grams, which basically means that if FeSO4, which according to our calculation is 3.39 grams, so the FeSO4 according to our calculation is coming out to be 3.39 grams. So this original sample of the salt, the rest of the mass is going to be made up of water. This is exactly what is being asked in part H. Using answers to A and G, calculate the mass of water in the sample of FeSO4. So our original sample of the salt The original sample of the salt is containing 4.96 grams. If we get rid of the FeSO4, the leftover mass is going to be of that of water. So it's going to be 4.96 minus 3.39 grams. So 4.96 minus 3.39 grams. And that would give you the mass of water. So using my calculator now, and the answer is 1.57 grams. So that is the amount of water that would be present in this sample. And now you're asked in part I, using your answer to H, calculate the number of moles of water in the sample of FeSO4. We've found the mass of water. Moles of water would be the mass of water, which is 1.57 grams, divided by the molar mass of water, which is going to be 18, because water has 2 hydrogens and it has one oxygen, so that would be 18. So finding the moles, dividing this by 18, and the answer that I'm going to get is 0.0872 moles. So that is the amount of moles of water that is present in the salt, in the original sample of the salt. In the next part, part J, using your answers to F and I, calculate the number of moles of water combined with 1 mole of FeSO4. So we knew the moles of FeSO4 from the previous step. The moles that we calculated were 2. Let's go back and have a look. When we were finding the mass, the moles that we had were 2.23 times 10 to the power minus 2 moles. These were the moles of FeSO4 that we calculated through our titration. So we have the moles of FeSO4, 2.23 times 10 to the power minus 2. And we also have the moles of water, which we calculated in this previous step over here. So that's 0.0872 moles. Now what we need to know is how many moles of water are combined with 1 mole of FeSO4. So using ratios, if you have 1 mole of FeSO4, then what is the amount of water that would be combined with that? So I'm going to use ratios, simple ratios, and the answer that I'm going to get is going to be, this is my unknown, this is what I'm going to calculate. The moles of water combined with 1 mole of FeSO4, and the answer I'm going to get is going to be 0.0872. X would be equal to 0.0872 divided by 2.23 times 10 to the power minus 2. And using my calculator to solve this, the value that I get is 3.91 moles. So for every 1 mole of FeSO4, the amount of water that's attached to it is going to be 3.91 moles. So we now need to state the value of X in the formula FeSO4.xH2O. Remember, in the very beginning of the question, he said that X is a whole number. So what we need to do is we need to round off the moles to a whole number, and the closest one is going to be 4, which means that for every 1 mole of FeSO4, there would be 4 moles of water attached to it. So the formula would be FeSO4.4H2O. According to our calculation, it was 1 mole combined with 3.91 moles of water. But since rounding off this 3.91 to a whole number, it gives us 4. In the next part, we've pretty much done the calculations related to moles. Now in the last part, part L, when iron 2 sulfate crystals are left to stand in air, a yellow solid forms on the surface of the crystal. And he's asking to suggest the identity of the yellow solid. Now, when iron 2 sulfate crystals are left to stand in air, iron 2 sulfate crystals would definitely react with oxygen in the air, and they would form iron 3 oxides, which would be brown. They're going to get oxidized in air. Iron ions will get oxidized. They will react with the oxygen. Oxygen is the reactive part in air, so they're going to react with oxygen. And iron 2 salts are green in color. They're greenish in color. Since he's talking about a yellow or a red-brown color, that would be most likely rust. It's going to be iron 3 ions. So the formula of oxygen combining with iron 3 ion is going to give you Fe2O3. And why is it formed? You're going to write that oxygen in the air oxidizes iron Fe2 plus ions. So they're going to get oxidized by oxygen. And then he's saying that the yellow solid is dissolved in water, aqueous sodium hydroxide is added, and what is seen. And in the last part, the yellow solid is dissolved in water. Remember, the yellow solid contains Fe3 plus ions, and he's forming an aqueous solution, and NaOH is added. Now, NaOH, sodium hydroxide, is a test for iron 3 ions, and if you remember the test for iron 3 ions, when NaOH is added, a red-brown precipitate would be produced. So that is a test for iron 3 ions, because iron 3 ions in aqueous state would combine with the OH ions in aqueous state as well, and they would form FeOH3, which is an insoluble red-brown precipitate. So a solid FeOH3 would be produced. So this is a test for iron 3 ions, and you need to remember the test for cations, that iron 3 ions, when you add NaOH, an insoluble red-brown precipitate is formed.